Welcome to Mydreamsacademy.
Good day, friends. Welcome to another episode of My Dreams Academy online tutorial. I'm your tutor, Eva Prime, and today I'm going to be teaching you about the joint interaction of electric and magnetic field, that is electromagnetic field. Okay, before I forget, please don't forget to subscribe to our YouTube channel and click the notification icon so that you'll be notified of our subsequent videos. Okay, so you might be asking yourself if there is an interaction between electric and magnetic field. The two things sound differently, but why do we have an interaction between them? Okay, now that question was answered years ago by a man named Michael Faraday. He was the person that was able to discover that there was an interaction or a relationship between electric field and magnetic field. Okay, and of course further experiments show that these two quantities are related in so many ways. Okay, and are also applied in different technologies used today. For example, in our generators, in our motors, in our dynamos, all these things are effects of what? Electromagnetic field. That's relationship between electric field and magnetic field. Okay, so we're going to be talking about, so we're going to start with basics. Okay, we're going to start with basics by understanding what happens to a charge when it is being projected into a magnetic field. Okay, so let's assume we have a magnetic field produced by a bar magnet. We have a north here and we have a south pole on this side. Now, of course, the lines of forces are as shown below, pointing downwards. Now, I have a charge, maybe an electron E. Of course, any charge we have must have a magnitude, and the magnitude of that charge is represented by Q. Now, it is projected into this magnetic field with a velocity V. Okay? Now, once this charge enters the magnetic field, it experiences a force. Okay? Probably the charge was moving on a straight line. If it was moving on a straight line initially, if it is being projected into this magnetic field, what happens? It will be what? It will be pulled by either of the poles. And because this charge is an electron, that is a negative charge, it will be attracted to the north side. If it was a positive charge, it will be attracted to the what? To the south side. So, but all we know is that it must experience a force. Okay? Now, if we call that force F, that force has a magnitude F equals QVB sine theta. QVB sine theta. Now, what does Q represent? Q represents the magnitude of the charge. V represents the velocity at which it is projected into the field, and then B represents the magnetic field strength. And then theta represents the angle which the charge makes with the magnetic lines of forces. Okay, let's assume it was projected at a particular angle. Look at the angle we are talking about. This is the angle theta, the angle between the charge and the magnetic lines of forces. Okay, now if you look at this equation now, let's see when the force becomes maximum. Okay, so when we project this charge into the magnetic field at an angle, we are going to have this force. Now, but let's assume that when theta equals 90 degrees. Now, when theta is equal to 90 degrees, what will happen to this equation? We're going to have F equals QVB sine 90. And we know that the value of sine 90 is definitely what? 1. And sine 90 is 1. Okay, so 1 times QVB gives us F equals QVB. Now, this force now, this second equation is called the maximum force. Okay, so the force is maximum. The force on the charge is maximum when theta is equal to 90 degrees. Okay, that means when the charge enters the field perpendicularly. Okay, now at another time, what happens? Let's assume that this charge was not projected into the field. In other words, let's say it is projected at an angle of 0 degrees. Okay, that means it was what? Projected parallel to the field. Okay, so if theta equals 0 degrees, if theta is equal to 0 degrees, the equation becomes F equals QVB sine 0. And of course, the value of sine 0 is what? 0. And of course, the force becomes what? 0. Okay? So that means that there is no force on the charge when it is projected parallel to the field. So it must interact with the field for it to experience a what? A force. Now, next up, we're going to look at the force on a current carrying conductor in a uniform magnetic field. Okay? Apart from looking at electrons now, because electrons, of course, they are not visible. But let's look at what happens to a conductor that is carrying a current in a magnetic field. Okay, so we're going to be talking about the force on a current carrying conductor in a uniform magnetic field. Okay, now as we can see, we have conduction rails. Look at the first one and look at the second one. and both of them were connected to an external source. Look at the positive, and this is the negative. And then we have a copper conductor. Look at the copper conductor that is normally used to complete the circuit. Now, what does that mean? It means that if you don't put this copper conductor, this is the conductor we're talking about, okay, there will be no current flow because the circuit will not be closed at that time. And of course, we have the magnetic field that is produced by bar magnets, though it's not in the diagram, but look at the lines of forces. Look at the arrows pointing upwards, meaning that we have a south on the top and we have a north somewhere below. Okay, so if I switch on the circuits, I will observe that a current I flows through the copper conductor. It is going to flow through. We look at the current I, it will flow through the conductor. And of course, because this conductor is in a magnetic field, it is going to observe that it will start rolling across the conduction rail. So that means that this guy will start moving, rolling across the conduction rails. That is what it can do. Now, but if you remove the magnetic field, of course, there will still be current flow, but this conductor will not be able to move. It will not be able to move. It won't move, okay? Now, but because there is a magnetic field, anytime you switch on this current, it will start sliding across the rail. It will start sliding across the rail, okay? And of course, if it is sliding across the rail, it means that there is a force responsible for that. Remember that is a type of motion. And according to what we know already, that to every motion, there is a force behind it. Okay, now this force we are going to be talking about, according to what you can see, the force is directly proportional to the angle between the conductor and the magnetic field. It is also proportional to the current flowing through the conductor. It is also proportional to the length of the conductor, and it is also proportional to the strength of the field B. Okay, now if you combine all these 1, 2, 3, 4, if you combine them, you will have a single expression. The force is directly proportional to the current, length, B, and the angle. Okay, and of course from mathematics, remove the proportionality sign, you're going to have F equals KIL B sine alpha. That is the angle. And then we now said where K is the constant of proportionality, and of course it will have a value of 1. If K has a value of 1, then we have a formula. So the force on a current carrying conductor has a magnitude F equals ILB. Okay, so from that we have been able to see that the force on a current carrying conductor is given by the formula F equals BIL sine theta. Okay, now we are going to be looking at when it is maximum and when it is minimum. Now from what we did previously, we said that let's assume that theta is equal to 90 degrees. Now, when theta is equal to 90 degrees, of course, the equation is going to change to F equals BIL sine 90. Definitely the value of sine 90 is what? 1. And of course, if sine 90 is 1, put it here, you're going to have F equals BIL. Now, but this is not just F, it is called F max, meaning maximum force. So if you've been asked, when is the force on a current carrying conductor maximum, you say it is what? It is maximum when the angle between them is what? 90 degrees, or when that conductor is perpendicular to the magnetic field. Okay, so we're going to look at the next one. If we assume that theta is equal to 0 degrees, now what happens? If theta is equal to 0, F becomes equal to BIL sine 0. Now what is sine 0? Is 0. So that F becomes equal to what now? 0. Now, what does that tell you? It tells you that if that conductor is parallel to the field, that means if it is an angle of 0 degrees with the field, then there is no force. There is no force. Even if there is a current flowing through that conductor, even if there is a magnetic field, there will be no force because it doesn't cut through the magnetic flux. Now, we're going to look at questions on that before we go to the next section. We all know that forces are vector quantities. And by vector quantities, we mean quantities which have both magnitude and direction. Now, we've talked about the magnitude of that force, which is given by the formula F equals BIL sine theta. Okay, now we're going to talk about the direction of that force. Now, the direction of that force can be obtained using what we call the Fleming's left-hand rule. Fleming's left-hand rule, okay, something like this. Now, the Fleming's left-hand rule states that When you keep the thumb, the index finger, and the middle finger of the left hand at right angles to each other, if the middle finger shows the direction of the current, index finger shows the direction of the magnetic field, then the thumb will show the direction of motion. Okay, now what does that mean? Look at my left hand and I bring my three finger. Look at the three fingers we're talking about. The thumb, the index finger, and the middle finger. Now, according to Fleming's left hand rule, it says that if I keep these three fingers mutually at right angles to each other, meaning that when they are placed at right angles, as you can see, now what happens? Then my thumb will point towards the direction of the force, that is the motion. My index finger points towards the direction of the word, the magnetic field. Then my middle finger will point towards the direction of the word, current. That is Fleming's left hand rule. Just practice that, okay? Okay, so we're going to talk about the fundamental concept of electromagnetic induction. Now, like I told you before, electromagnetic induction was discovered by Michael Faraday while he was experimenting on things. Now, let's see. Now, to repeat some of those experiments, we're going to use what we call a solenoid. A solenoid. Now, if you don't know what a solenoid is, it is actually what? A cylinder, a hollow cylinder on which a coil of wire is wound. Okay, now what does that mean? I get a hollow cylinder, look at the hollow cylinder, and then I make coils of wire on it. I make coils of wire on it. Now, so if we assume that this marker is a hollow cylinder, hollow means that there is space in between that I can slot in my hand and maybe I can see it from here. And then I make coils of wire around that cylinder. It forms a solenoid. Now, once I am done with that solenoid, I will connect it to a galvanometer G. Okay, a galvanometer G, which has a center zero deflection. And then, look at what I have. Now remember, a galvanometer is a special instrument used for detecting little amounts of current. So anytime you have in a circuit a little amount of current and you want to be able to detect it, you don't use an ammeter. Okay, so you use what we call what? A galvanometer, because of the little amount of current. Now, once I have connected it this way and then I have a bar magnet. Now it is observed experimentally that anytime I am moving this bar magnet close to this coil, if I'm bringing it very close, what happens? It starts deflecting. This galvanometer starts deflecting. Now what does that mean? If I move this bar magnet close, there's a deflection. Or if I keep the bar magnet stationary and move the coil close, there is also what? A deflection. Okay, now let's see, how does that happen? Now, according to the explanation, that if I am bringing this bar magnet very close, the magnetic lines of forces comes out of the bar magnet. Okay, now when they come out, they will go and link up with the coils of that solenoid. They will go and link up. It is called magnetic flux linkage. Flux linkage, okay? Now, so the magnetic lines of forces will cause a flux linkage. Now, that flux linkage is what is converted into current that is deflected or seen by the galvanometer. In order to understand it in detail, we're going to talk about what we call the Faraday's law of electromagnetic induction. Now, according to that law, that an EMF is always induced whenever there is a change in the magnetic flux of a magnetic field. Okay, and the magnitude of that induced EMF is directly proportional to the rate of change of the magnetic flux. Now, what does that mean? Now, according to Faraday's law, Faraday says that for an EMF to be induced in the galvanometer, that means if we are supposed to have a deflection in the galvanometer, what must happen? That there must be a change in the magnetic flux. Now, what does change means? It means that this field must not be a uniform field. That means it must not be flowing at a constant rate. There must be a what? A change. There must be a change in that what? Magnetic field. Okay, there must be a change. And for us to produce change in that magnetic field, there must be motion. Okay, now what does that mean? Meaning that I can move the bar magnet to and fro, or I move the coil to and fro to produce a change in that magnetic field. Okay, so that is what Faraday's law is trying to tell us. Now, Faraday's law also said that the magnitude of that induced EMF is proportional to the rate of change. So, how fast, if I want to produce a what? A large induced EMF, what do I need to do? I need to what? Consider how that field is changing. How fast the field is what? Is changing. So, if I want to produce a large deflection on the galvanometer, I need to rotate or move the magnet very fast or move the coil very, very fast to produce a large induced. So this Faraday's law can be summarized in a particular formula, which is E equals minus N d phi dt. Now, if you look at this formula, we have d phi dt. Now, what does d phi dt represent? This represents the phi represents the what? The flux. Okay, so d phi dt means the rate of change of what? Of magnetic flux. Of course, it changes with respect to what? To time. Now, N here represents the number of turns of the coil. Now, as you can see for the solenoid, it has several turns of wire. Okay, so the number of turns of the coil is our N. Now, this minus here is actually from what we call Lenz law. Lenz law. Okay, now so that means that Faraday's law is not complete without knowing what Lenz law is all about. Okay, but whenever we consider the magnitude of the induced EMF or current, we use what we call Faraday's law, and it is given by the formula here. Now let's talk about Lenz law. Okay, now we're going to talk about Lenz law. Lenz law. Now the statement of that law says that whenever there is an induced EMF, it moves in such a way as to oppose the motion producing it. Okay? So the induced EMF moves in such a way as to oppose the motion producing it. So imagine a situation whereby you're pushing a desk. Normally, it is supposed to move in the direction where you're pushing it. Now, but the induced EMF moves in a what? In the opposite direction. So that means that if that chair or that table was the induced EMF and you are pushing it, instead of moving in the direction you are pushing it, it is moving in the opposite direction. And why is it moving in that opposite direction? To oppose that motion that you are giving to it. That is what Lenz law is trying to say. Now, to explain that from this diagram, imagine that this bar magnet is moving close to the solenoid. Now, if I am moving this bar magnet close to the solenoid, what happens? The end, assuming, okay, let's call here A and call here B. Now, the end A of this solenoid will gain a what? A north polarity. It will gain a north polarity because I am moving the north pole close. So, end A here gains a north polarity. And why will it gain a north polarity? So that it will oppose the motion of this magnet. Okay, it will oppose the motion of this magnet. And how does it oppose? Remember that this is north and this is north. North, will they attract or repel? Definitely they are going to what? Repel. Okay, so according to Lenz law, what happens? If I am bringing a north pole of a magnet very close, the end A gains a what? A north polarity, so that as it is coming close, it is trying to push it away. No! Go back. Okay, now if I reverse the condition, I still have my solenoid. This is my solenoid. I have coils of wire around it, coils of wire, and then this is my galvanometer. Now, but in this instance now, I am bringing a what? The south pole of a bar magnet close. So if I'm bringing the south pole of a bar magnet close now, what happens? This is my NA and this is my NB. Now, of course, according to Lenz law, it moves in such a way as to oppose the motion producing it, right? So what happens? For us to oppose this motion, what happens? This end is supposed to gain a what? It gains a what? A south polarity also, because I am bringing it what? Close. I am bringing it close. So NA also gains a what? South polarity, so that it can repel it. Okay, to oppose the motion producing it. Now, what if I was actually bringing, okay, this is a north pole, but this time around I am moving it away. I am moving it away. So what happened? I am moving a north pole away from this side. And how does it happen again? According to Lenz law, it will move in such a way as to oppose the motion producing it. So if I'm taking a north pole away from this end now, which polarity will be at this end? Yes, it is a what? South pole. A south pole will be here. Why will a south pole appear here? So that it will oppose the motion of this. And for it to oppose, it needs to attract it. Okay, so if I'm taking the magnet away, the end A gains a south polarity so that it will oppose the motion of this guy. Okay, so that is the illustration of what? Of Lenz law. Now, when you combine Faraday's law and Lenz law together, it is what we call the laws of what? Electromagnetic induction. Now, these laws are what? Are applied in several appliances we use nowadays. In our generators, okay, like the generator using your, that is an AC generator, it applies Faraday and what? Lenz law in its mechanism. Okay, so we're going to be talking about the generators, the DC generators, the AC generators. We're also going to talk about how to measure AC and also how to measure what? DC and other applications of electromagnetic induction.
Welcome to my Dreams Academy.